personal relationships on the Commonwealth. So, Mark has a long history of studying the coordination between the visual and vestibular systems, and from 2013 to 2016, he served as the chief scientist of the NASA Human Research Program, where he was instrumental in adopting interdisciplinary approach to managing health risks in space. Mark's human spaceflight lab currently works to explore astronaut adaptation and resilience in space, and they host an ever-engaging human spaceflight happy hour 3 times a month that is, I think, really how we first started talking. And so it's my distinct pleasure to welcome Mark, and he's giving the talk that is the best name of any talk that I've ever seen. So,
thanks, Mark. Thank you, Mike. Thanks, everybody. So yes, I'm going to tell you, I'm going to wander around a little bit, so I hope you can see. If I get too far from the mic, somebody wave or whatever. So I'm going to tell you about my point of view, anyway, about how to send people to Mars without killing them. And clearly, I'm not going to talk about propulsion. I'm not going to talk about spacecraft design. I'm not going to talk about all those really interesting engineering and operational things. I'm going to talk about what is both the hardest part, the part that makes a spaceflight mission the most fragile and subject to failure, but also the part that at the same time can lend it the most resilience and robustness. And that, of course, is the human crew. Right? The human crew are arguably the most fragile components of the whole thing, but if you design the mission properly, which is what I'm going to talk about to some extent, you take advantage of the capabilities that humans bring, so that you actually make it worth the trouble that it takes to accommodate humans. Because make no mistake about it, they are kind of messy. They do screw up the pristine engineering designs put into place by the operational people and designers. So why do I care about Mars? I mean, really, are we really talking about Mars seriously here? 10 years or so ago, you couldn't really do that. People have been talking about going to Mars forever. But still, it was in the realm of science fiction. Nobody seriously was talking about going to Mars. Well, thanks to Elon Musk, among others, we can now talk seriously about going to Mars. It's going to happen. It's going to happen within the lifetimes of many of you in this room, maybe even my lifetime, if people get their act together quickly enough. So one of the reasons that I, in particular, am thinking about sending people to Mars is because of the time that I spent with NASA. The NASA word, the NASA thing there, of course, has a $ sign on the yes, which means I was getting paid to think about sending people to Mars. That was NASA's next big goal during the time that I was there, 2013 and 2016. Now it's been diverted a little bit. We're going to go back to the moon first, and then maybe sometime go back to Mars. So that's both fortunate and unfortunate. We can talk about the relative benefits and costs of going to the moon versus Mars after my talk. But the idea of going to Mars really focuses the mind. There are some things that you can get away with. Going into space is hard no matter where you're going. Low Earth orbit, very challenging. Of course, the moon, extremely challenging, dangerous. So I'm not making light of any of those, but compared to sending people to Mars, they're relatively simple. You can afford to overlook some things, and because of the relative proximity, both in distance and time, to Earth, when you're in low Earth orbit, or even when you're at the moon, you got a lot of help from Earth. You can resupply, you can come home if there's a problem. When you're talking about Mars, all those things are off the table. It really makes all of these problems very acute. I'll talk about some of those in detail. Also, when you're talking about Mars mission is probably going to be 3 years. About a year, about 9 months or so on the way out, same on the way back, and a year to a year and a half on the surface or in orbit around Mars, whatever. So 3 years. So you're not talking about building a vehicle that they just travel in. You're talking about building a vehicle that they live in. You're talking about creating the world for those people for those 3 years. So all the things that you value in your life, like leisure, recreation, to maintain an even strain so that you can work with the other people in close confines, all those things have to be thought about and accommodated to some extent. So we're designing not just the spacecraft, but the world for those crews. And the reason we're going is because we expect that there will be things that we don't expect. There will be unanticipated findings, including unanticipated events that will impact the health and safety and performance of the crew. If this wasn't the case, there's no point in going if we're not going to see things that we didn't expect. So there will be unexpected things, but we can't think of them all. So this is going to be one of the key themes of my talk, especially near the end. Down at the very last part, it includes, a Mars flight includes everything. I mean, all the things that we need, that we value for life in a dangerous environment from high-performing individuals. They're called on to perform a mission. So it includes a whole bunch of things, and yet we can't think of everything ahead of time. So the big job of people thinking about how to send people to Mars without killing them is not just to make sure that they don't literally die, but to make sure that they have the tools, the resilience that the mission designers can provide so that they can solve problems on their own, so that they can take care of themselves without having to rely on help from Earth. So in that sense, it's also a laboratory for dealing with the complexity of life. Just, it's no accident that I am in a laboratory that does the same thing. So there are very close ties between terrestrial medicine aspects and going to Mars, frankly. Okay, a little bit more. So this is what I just said. You can think of a Mars flight as an analog for some of the terrestrial concerns. I'm not going to read down that list. But sometimes I get pushback from some of my colleagues in the conventional medical sciences, of which a place like Johns Hopkins Medical School is full. So I get all these people who are, let's call them NIH-oriented researchers, not really NASA-oriented researchers. And they will say things like, well, you know, what's the point of studying people in space? Astronauts are very much unlike the larger terrestrial population. They're extremely fit, they're of a certain age range, they're very compliant, they eat well, they exercise. So how is any of that stuff transferable to terrestrial care? And, oh, by the way, if you didn't send people into space in the first place, you wouldn't have to study how they adapt to being in space. So therefore, why don't we just send robotic missions all the time? And it completely misses several very interesting points. One of them being we're sending people into space because to meet and deal with the unexpected. So you want people to be there to increase the resilience and scientific return, exploration return of your mission, but also it provides an opportunity to simplify many of the confounds that you get when you do terrestrial research on populations in real-world settings. So all the things that I just described about astronauts being of a specific age range, we know what they eat, we know how much they sleep, we know how much they exercise, we know what they're doing, we monitor their performance, not as much as some of us would like, but to a large extent, we know when they make a mistake. You can't do this in most normal terrestrial settings. Maybe you can do it here for a limited time, but here you've got a 3-year opportunity for people out, let's not say in the real world, but in a demanding environment that calls upon to make real-time decisions under challenging circumstances. So it's a laboratory to figure out how people do that on Earth as well. So I look at it as a way to bring spaceflight research results back to Earth, back to terrestrial medicine. So in some ways we can study this in space better than on Earth because we remove some of those confounds. And I sometimes say, if we can't figure this out in space with the removal of all those confounds in an environment in which everything is monitored, we know what the atmosphere is, we know the radiation, we know all those things. If we can't make some progress in figuring out what makes people resilient under demanding circumstances in a setting like that where everything, including the crew, is monitored, then we're probably not going to be able to make much progress on that on Earth. So let's hope for all of our sakes that we can make progress on it in space. Okay, don't worry, I'm going to get to the interesting slides that actually have pictures and data and stuff like that in a couple of minutes, but I'm just trying to lay the groundwork here for this, so you need to see where I'm coming from. So my major premise here is that in order to figure out how to send people to Mars without killing them, maintaining health and performance is a key thing here, right? It's not just sending people to Mars and making sure that they live, it's sending them to Mars and make sure that they can get their jobs done. Otherwise, there's no point in sending them to Mars. You're sending them there to do a job. So health and performance are both equally important, I would say. Not that we're cavalier about their health, but you're sending them there to do something. So health and performance, but in order to do that in this particular circumstance, we have to start breaking down discipline-specific silos, of which I'll give you a couple of examples. But just as one example, what happens here on Earth if you go to get medical care for an issue and you see your personal physician? Well, chances are the next thing that person does is send you to a specialist, and then maybe another specialist, and then a specialized care facility, and maybe an imaging facility, whatever. You can't do that in a space flight. So you have to treat the individual holistically and recognize that you're not, in many cases, going to be able to provide tertiary level care, prime gold standard care that you would get on Earth. So you have to accommodate that into the medical system. But part of that means we need to understand the interactions between the different physiological systems, holistic approach to health, because you can't afford to wait until one of them gets really bad and then treat that. The interaction between physiology, psychology, we know that those connections are there, stress effects on physiology and behavior, and then engineering and operations. This is the connection that is frequently not made by people thinking about this. And you've got the human health and performance community, largely, and the engineering and operations community. And as we would say for a long time, this is changing, but the attitude used to be, to a great extent, that the engineers design the spacecraft, and then they think, oh, we're going to put these pink squishy things inside this thing. They're going to mess everything up. You know, they're going to be whatever, vomiting, and they create waste products, and nobody told us we're going to put humans in there. So human-centered design, accommodating the needs of the human crew, which not only means accommodating their needs, but also accommodating the fact that they can contribute, properly designed, to the maintenance and resilience and robustness of the spacecraft and the habitat itself. So it's a two-way thing. You don't want to treat them as just these little things that you plug in as an afterthought at the very end. Many people still think that way. So we don't have the luxury of terrestrial resources. I've talked about that, including medical care, including time to think about issues. So crew autonomy will be an issue. But here's a point that not everyone agrees with. From my point of view, when you have people in space, you don't need to understand all aspects of human health, performance, physiology, psychology in the way that you would be doing it in a scientific study in a laboratory. You need to know enough to make sure you understand when things may be going wrong, to apply some corrections or maybe advise the crew, or maybe just raise a red flag that says, Commander, there's something, my artificial intelligence algorithm has detected something strange going on here. I can't tell you the details. I'm not smart enough to tell you the details, but I can tell you something is amiss. So the idea of just providing broad stroke information, feedback to the crew for early warnings can be extremely valuable because they will act on that information. They're very obedient in that sense. So we need to understand enough to at least not inhibit the resilience of the crew, and then provide information for the crew to work it out among themselves. So now let's talk about some of the details, now that you understand where I'm coming from. So currently, NASA has, I'm talking about NASA a lot because that's what I'm familiar with. We're in the United States, so NASA is running the show largely. But you know, the Chinese have people in space. There is a Russian space program. There's a European Space Agency. There are other space programs around the world. we're going to be talking about largely about the NASA approach. And of course, there's commercial space flight as well. Elon Musk might lead everybody to all of those to Mars. So right now, NASA and its international partners has the International Space Station, low Earth orbit, about 250 miles or so up in space, and crews go up there typically for about 6 months at a time. So right now, a crew just went up, and I don't know if they've docked yet. It takes about a day to get there. Once they dock, there will be 6 or 7. It's a little confusing now because now that SpaceX is flying people, they can fly 4 rather than just 3 like on a Soyuz capsule. At any rate, 3 or 4 people go up. At about the same time, 3 or 4 people come down. So there's a 3-month rotation, but each individual typically will stay on the space station for 6 months. So we have a really good database of what happens when you have people in low Earth orbit for 6 months at a time. We have a few data points about people being in low Earth orbit for a year at a time. The Russians and the Soviet Union have more experience with that, but it's still not a lot. The number of people who spend a year in space is really very small, less than 10 probably. But the thing about being in low Earth orbit is, even though, like I said, it's still space flight, it's still dangerous, it still has a lot of risks involved, but you're relatively close to home. If there's an emergency, including a medical emergency, the crew can abandon ship, get into the spacecraft, be back on the surface of Earth within a matter of hours if they need to. So that influences the mindset about how much autonomy you need. Even if you don't have to call upon that need, it's there, you know, that you can do it if you have to. There's strong consumables resupply every few weeks or months. The supply ship goes up, takes some fresh food, letters from home, metaphorically at least, things that will help the crew get along and feel like they have fresh supplies. And real-time communication. Whether the crew wants it or not, and sometimes they really don't want it, mission control is always there to lend a helping hand and give them some advice. On the other hand, mission control is always there as well in case they need a medical consultation or a psychological consultation. So they can essentially pick up the phone and talk to somebody on Earth anytime. When you go to the moon, which is the middle set here, the second one down, near real-time communication, it might as well be real-time communication, a couple second time of communication lag at the distance of the moon, about 250,000 miles away. Evacuation capability, still pretty good, but now getting a little dicey if there's a real medical issue. Could be 3 to 11 days to get back. Really only takes about 3 days to get back from the moon, but the orbit that NASA is anticipating for the gateway, the lunar gateway that will provide the habitat in orbit around the moon, is going to be on a highly eccentric orbit, at least as they plan now. So until that gets back around, where the crew can get back from the surface of the moon up to it and then get back to Earth, could be on the order of a week and a half. But still, they can come back home if they need to in a medical emergency. Limited consumables resupply because it's so far away. It takes longer to get there. But when you're talking about Mars, Mars is a whole different story. No real-time communication. One-way communication lag from Earth to Mars is on the order of 20 minutes. So you have a medical emergency and you call home, you get your answer 40 minutes later, assuming that Mars and Earth are not on opposite sides of the sun at the time, in which case you're never going to get that answer. So crew autonomy takes on an extremely large role here. You've got to give the crew the tools to fend for themselves. No evacuation capability, and this extends not only to being at Mars, but due to propulsion limitations and trajectories, orbital trajectories, and things that I don't understand. Once a Mars mission gets to a certain point, that mission is going to Mars, and the spacecraft is going to be there for the year to a year and a half or so until the planets Earth and Mars line up again appropriately so that the crew can get back with the propulsion capability that they took with them. It is not the case that you can get halfway to Mars and change your mind and come back home. So what happens? It's going to be a 4 or 6 person crew, most likely, going to Mars. One of those people gets an intractable disease, illness, or injury halfway to Mars. You're not coming home. You're not turning around. You are making the decision as to whether I'm going to use half of my medical supplies, or what about the rest of the crew who might need some of those medical supplies? There's a very real chance that somebody might not come back alive. There's a chance that somebody might not even make it to Mars alive because you have to make these medical decisions. So clinical decision support is part of the autonomy that we have to grant to the crew to make those kinds of decisions. They're not going to be easy if that should happen. I'm not trying to cry wolf here. I'm just giving worst case scenarios that people should be prepared to deal with. And for obvious reasons, no consumables resupply. It's just too far away. So either what the crew takes with them on their spacecraft or what is pre-positioned years ahead of time, likely, because again of the planetary alignments. So what is there waiting for you, and what you take is what you get. So don't expect to be getting supplies of fresh fruits and vegetables from Earth while you're at Mars. So this is all a form of increasing crew autonomy and increasing exposure to hazards. It gets more and more dangerous at the same time the crew can depend on Earth for less and less help. So what is NASA and its international partners, among others, what are we doing about this as a community? Well, a lot of research on the International Space Station, some of which I'm going to tell you about now, and then I'm going to cycle back to the whole resilience effort. So the International Space Station, low Earth orbit, permanent human presence in there for more than 20 years now, which would have seemed like science fiction when I was your age, to have people in space continuously for that long period of time. Not the same person for 20 years, obviously, but a whole big turnover of people, NASA astronauts, international partners, Russian cosmonauts, among others. And this is an example of some of the stuff that goes on inside the International Space Station. This is a busy place, like I said, and it's getting old, so there's a lot of operations and maintenance going on just to keep the place functioning, the International Space Station. But apart from that, apart from maintenance and operations, at least last time I was told this, the Human Research Program at NASA is the single biggest user of crew time, except for operations and maintenance, on the space station. Crew time is the most valuable resource. Crews are extremely busy. NASA does not send astronauts up to just look out the windows. They send them up there to do things, including Human Research Program experiments. So this is an example of some of them. So you can see in the middle, there is obviously, I wouldn't be surprised if that's an HRP experiment of some sort going on. You see he's on a cycle ergometer, measuring gas exchange. He's breathing in, what he's breathing out, electrodes on his chest, on his body, to measure metabolic activity, heart rate, things like that. On the left-hand side, you can see this was part of the so-called one-year mission and also the twin study, which got some press a few years ago. So this is astronaut Scott Kelly doing an ultrasound on his eye. Why is he doing ultrasound on his eye? I'll tell you about that in a few minutes. He's assisted by Mikhail Kornienko, who flew with him on the one-year mission. 340 days, close enough for NASA's work to call it 1 year. And on the right-hand side is, again, Scott Kelly. Here he's giving himself a flu shot. Why? Are they concerned about getting the flu in space? No, they are not. This was a titrated perturbation of his immune system. This is part of the NASA twin study. Scott Kelly, who you're seeing there, has a twin brother, Mark Kelly, who was a retired astronaut at the time. So this was one of NASA's initial forays into the omics field, genomics, proteomics, because you had two genetically identical individuals, one staying on Earth, one going into space. Okay. Now, this is the lightning round here, where I'm going to tell you about some of the things that happen when you send people into space. This is the boring slide because this is the one that just goes a smatter of things. I'll go into detail, a little bit more detail on some of the more interesting ones, but some things that you don't really think about in normal life. Food and nutrition. Well, for Mars specifically, you got, like I said before, you got to have a plan to either pre-position or take food that provides nutritional content, all of your nutritional needs, for 3 years. And that includes food that may be pre-positioned on the surface of Mars and has to withstand the radiation environment that's present on the surface of Mars, which is a lot harsher than it is in low Earth orbit or on the surface of Earth. So you have to think about that. Food, by the way, is absolutely critical, obviously, for nutritional needs, but food is one of the few comforts of home. Otherwise, the spacecraft can be a pretty sterile type of environment. There's not a lot of green stuff up there. You can't look out the window. Even on a day like today, it may be still pleasant to look out the window and see nature, see trees, see leaves, see greenery. You don't have that on a spacecraft. What do you have? Well, at least you can have a hot meal with your friends and colleagues. Right? That is a bonding experience. So food not only provides nutritional needs, it provides it satisfies huge psychological needs. There are stories, classic story, anecdotal, but classic stories of crews on the International Space Station. They tend to scatter to the different parts of the station during the day while they're working on their individual activities. But it's not unusual, as I understand it, for the commander to say, I don't care whatever else it is that you're doing, we will have, as a crew, have one meal together every day. We will congregate in the galley and have dinner together. It's like, when you're growing up and your mother says, you will be home and we will eat as a family. This may be the only time we see each other during the day. Extremely important for bonding. They find any excuse they can on ISS to celebrate holidays. Somebody's birthday, it's May Day in Russia, it's this or that, because that's another excuse to have a little bit of a party. It's a bonding experience. These things take on extreme importance when you're in an environment with your normal comforts of home removed. Okay, turning to the more of the fundamental physiology issues, this is one that people tend to hear about and ask about. Bone mineral loss of bone mineral density. I'll show a slide about this in a little while, but it's to make a little bit different point. But when you go into space, what are the main things that happen? Well, there's an increased radiation environment, isolation and confinement, psychological issues, but the big one for physiology is you don't have a gravity vector. Right? So right now, I'm fighting against gravity just to stand. So my bones are loaded, my muscles are working to maintain upright posture, my heart is beating to maintain blood pressure to my head, hopefully. So all of these things are natural exercise just for moving around in 1G. You don't have that when you're in space unless you have artificial gravity or you're on a planetary surface where you have partial gravity, fractional gravity. If you're in orbit or on your way to Mars, then you're in 0G or weightless conditions, so you don't have that. So the body is very efficient at not carrying out metabolic processes that it does not need. So it starts to shed bone mineral density. The astronauts excrete calcium in the urine. Oh, that's interesting. So not only do the bones start to weaken if they're not careful, exercise is a good countermeasure. We're not sure if it's good enough yet, but also the calcium can get into the urine, it's excreted to the urine. So what happens there? Well, you increase the potential risk of getting kidney stones. You do not want to have a kidney stone on Earth, and you certainly don't want to have one in space. The treatment options are limited in space, to say the least. So this is an example of a synergistic risk, all right? You're in space, you're losing calcium from the bones, and not only impacts the bones, it impacts kidney stones. Well, those are two different medical specialties generally on Earth, right? The bone people and the kidney people. Well, here's just one example of which those issues really need to be addressed together. Human system interaction, how is the crew getting along with all of the automated and semi-automated things on the spacecraft, of which there will be many. If you travel half as much as I do, then you're used to renting cars on a regular basis. Every time you get into a rental car, you try to take stock of where you are because the devices and controls are a little bit different from the previous rental car. When can I depend on that car to get me out of trouble by telling me when somebody is in my blind spot? And when am I now in a car that's not going to give me that information? But I think it's going to give me that information. So mutual dependence, trust in automation, that's going to be huge because these missions are going to be incredibly complex. And this may change over the course of the mission. So what the crew may need later in the mission, after the fatigue, after they've gone through psychological, I won't say trauma, but the psychological stresses of being in isolation and confinement, they might want more help from the automated systems. So that has to be titrated to the crew's needs. You can't just solve it. One size does not fit all. Pharmaceuticals, same idea as for food and nutrition. Pharmaceuticals for 3 years. What's the shelf life of the medications that you have in your medicine cabinet at home? I don't think that it's 3 years. Why should it be? There is no incentive for pharmaceutical companies to test medications for extremely long shelf lives. Why? Better off throwing it away and buying a new one. It's a profit scheme. But for NASA, they need to be able to figure this out, especially if the medications are pre-positioned. You want to take a bunch of them, send them to Mars ahead of time, and the enhanced radiation environment, not only time. There are changes in immune system function. It's like every system in the body is affected by being in space for a long period of time. There are changes in function of the immune system that we don't quite understand. There are changes in T cell function, cytokine profiles, latent reactivation of latent viruses, of which herpes is one of them. This doesn't mean that they get herpes or these other, it just means there's a reactivation of the viruses that have been latent in many of the astronauts. This is not unusual. It does not reach a clinical threshold, as they say, so it's not clear if this has any real meaning or something we should be concerned about, but it certainly is unusual, and it's the kind of thing that gets NASA's attention, because so far, for 6-month and 1-year missions, it has not been a clinical issue. But what happens in a 1.5 years, 2 years, or 3 years? You don't want to find that out on your first 3-year Mars mission. So, changes in the gut microbiome, all these microorganisms that live in your intestinal tract and GI tract, which have different DNA than you. They are not part of you. They are separate organisms, but there's more of them than there are of you, more of those cells than there are cells that make up your own body. That microbiome changes during space flight. We don't understand exactly why, what its implications are. But the microbiome does a lot more than just aid digestion. There is the gut-brain axis, as it's called. So some aspects of cognitive function are also manifest through the microbiome and the health of the microbiome. One of the concerns here is that it's what's called the biome of the built environment, I think, something like that. But basically the idea is that as buildings like this become more energy efficient, part of the way they do that is by sealing them off from the external environment better and better. So what happens then? Well, you've got to pay a lot of attention to recycling these. Like being in an airplane, you have to pay a lot of attention to recycling the atmosphere. But what if you were to close all the doors here and nobody left the building for 3 years? Well, now you don't have the opportunity to go out and challenge your immune system with external stressors, and you're not getting a natural change turnover in the microbiome by experiencing other organisms that are out there. It's just what you see here is what you get. Does that have devastating or bad long-term consequences? We don't know, but it's possibly not healthy. Sleep is disrupted for a number of reasons, including the stressors when people are in space. There are some signs that there might be cardiac arrhythmias. Not a lot of evidence in that case, but it's one of those things that's low risk, but the consequences could be extremely bad if somebody has a heart condition while they're out exploring. Okay, so let me go 2 or 3 of these things in a little bit more detail. So the reason that Scott Kelly was doing ultrasound imaging of his eye, and he's not the only one. This is an ongoing set of research projects that NASA and the international partners have going on to investigate something called spaceflight-associated neuroocular syndrome. So there are some what we call weasel woods in there, right? It's associated with spaceflight, and it's a syndrome. We don't really know what this thing is. It's neuroocular, meaning, well, okay, it affects the eye, it affects vision, that much we know. Seems to maybe have some neural effects too. Well, we're not quite sure about that yet. So is this a big deal or is it not a big deal? Depends on who you ask and when you ask them. But this was found, I don't know, 8 or 10 years ago when some of the astronauts were coming back and reporting that they were having difficulty reading their checklists after being in space for a few weeks. Actually, it was only when they started flying people for 6 months regularly that people started to notice this. And you know, for an astronaut to admit that he or she is having a problem like this, that's a pretty big risk because they're very reticent to share medical concerns because it means they may not get to fly again. But enough people noticed it and were concerned enough about it that NASA started to pay attention to it. And sure enough, they found some things, and this is still, like I said, this is still going on, not at all a done deal. I'm going to describe what has been, and I think still is, the prevailing hypothesis for this, but it's a hypothesis. So the hypothesis is based on the fact that we know that there is a headward shift of fluids when people go into space because there's the lack of the gravity vector pulling fluids down to the bottom of my body from which the heart has to, among other systems, has to pump against that gravity vector. So you go into space, and it's more like being supine when you go to bed. You notice if you have a cold and your sinuses are congested, they get even worse when you go to bed because the fluid redistributes. So cerebrospinal fluid, blood, lymphatic fluid, all sorts of fluid will redistribute themselves toward the upper part of the body when people go into space. We've known this for 60 years, since people have been going into space. They have sinus congestion, it affects their taste and smell. And here's a picture of Story Musgrave, legendary astronaut, on the left on the ground, on the right in space, puffy face, very common. So we know that this goes on. What we didn't realize until relatively recently, because of this, this SANS problem, is that there might or might not be an increase in intracranial pressure, the pressure of the fluid, cerebrospinal fluid, that surrounds the brain and spinal cord, because the fluid works its way out, it redistributes itself, it's in the head, but the skull does not let the fluid out. So it's encapsulated around the brain, increases the pressure on the brain. There's a relief valve for that fluid. The relief valve seems to be for the fluid to work its way down the sheath of the optic nerve, which does not sound good and really is not good. So it works its way down inside the myelin sheath that surrounds the optic nerve, impinges on the back of the eyeball, and one of the things that is seen in imaging is down here where it says globe flattening. That means the globe, the ocular globe, the eyeball. And you can see that these have been enhanced, obviously, with that yellow line, but on the left-hand side, the normal image, the round eyeball, and on the right-hand side, it's as if somebody had, it's like pushing on a beach ball, gets flattened and squashed. That will change the optical properties of the eye, obviously, because you change the distances. That will change visual acuity. This, like I said, is the prevailing hypothesis. There are some other lines of evidence that lead us to believe that this is what's going on, but there are some alternative hypotheses too. But the point is, if you're increasing intracranial pressure around the brain, that cannot be a good thing over the long term. So sure enough, there's some other results, imaging studies, looking at the ventricles, which are the parts of the brain deep inside the brain where cerebrospinal fluid is created and stored. And you can see that this is a recent result, 2019. This is the size post-flight compared to pre-flight, because you can't do these imaging studies in flight, at least not yet. This is the size of the ventricles, those fluid-filled cavities within the brain, in astronauts as a function of time spent in space. And what do you see? Well, what you see is that they get bigger the longer the mission goes on. Why is that? Is it because more cerebrospinal fluid is being produced and not properly distributed? or is it because it's being distributed up toward the head and making its way into the ventricles and being stored there? Either way, that's another possible mechanism to increase pressure on the neurons, the neural structures in the brain, which is possibly bad over the course of 3 years, but we don't know yet. Astronauts do cognitive challenges when they're in space. There is objective testing does not show it, so when they're actually asked to do cognitive testing, which they do on a regular basis, they do perfectly fine. They're very high-performing individuals who will work themselves up to the level that they need to perform well on a test like a cognitive function test. But that doesn't mean that there are other things, that there aren't other things going on. So if you were to do dual tasking tests or test them in a more challenging situation, you might find decreases in cognitive function. Astronauts have reported for a long time what they call the space stupids, or sometimes space fog, this sense that they're having to mentally work through molasses, that things just seem harder to do. You know, I'm kind of forgetting things or losing track of stuff, but they get the job done. So far it hasn't been an operational thing. Now, with all the stresses of being in space, right, isolation, confinement, high workload, disrupted sleep, you're not eating well, nutritiously, but you're not eating normal meals, huge number of stressors. So is it any surprise that they might have some cognitive repercussions, or is it due to a more direct effect of something happening to the brain? We don't know, but this is a concern. I'm going to skip that one. Let me talk about this one. This slide's getting a little dated now, so I need to check whether it's been updated. This was supplied to me by David Dinges a number of years ago, who does sleep and performance research at the University of Pennsylvania, and he had astronauts, a small number of them, report on a visual analyzed scale, VAS, from 0 to 100. Tell me about your stress. Just give me a number. Whatever you mean by stress at this particular point in time, on whatever scale is meaningful to you. I mean, it's a very crude measure, but you can see what he found. Over the course of time, over the course of up here to 180 days, a 6-month mission, stress is not going down. Whatever they mean by stress is building up over the course of the mission. And Dave Dinges, being a good researcher who wants to get more money to do this research, was good enough to fit a cubic polynomial to this, which shows that when you get out to 1-year missions, the stress is going to be off the scale. Now, we don't know if that's the case or not. They may start calling on alternative coping mechanisms to deal with the stress. So we don't know how bad this is going to be, but it can't be a good sign that they're reporting a stress level that's increasing over the course of the entire mission, up to 6 months at least. Okay, here's the bone mineral density slide, and the bone mineral density story here is actually pretty simple. I can explain this pretty quickly, but I have another point that I need to make. But let's just look at the part over here on the right-hand side that's in the red box. So that is bone mineral density measured by DEXA scans, if you know what that is, from the pelvis. And this is an indication, the different colored symbols, of improved countermeasures over the course of time. That is, over the course of decades of improvement. And you can see, so let me see, the blue ones on the left are in the Soviet Mir space station, so this was in the 1990s, and it works its way up to the symbols on the right, the triangles on the far right-hand side, which is exercise on the space station. There's something called the Advanced Resistive Exercise Device, ARED, which is a resistive exercise device, coupled with bisphosphonates, which is a medication that's used for osteoporosis treatment. And you can see the key point here being, look at the 0 line there, about a little bit more than halfway up. That's the line that indicates no change in bone mineral density over the course of a 6-month space flight. Well, this countermeasure works pretty well, right? The final countermeasure. Some of these people come back with improved bone mineral density. Well, how can that happen? Well, they exercise 2 hours a day, 6 days a week on the space station. Not every astronaut does that on Earth. So some of them have never been healthier when they come back because of that exercise regimen. But the key point that I want to make here is look at the variability. You're lucky if you're the person who's got the symbol at the top. If you've got the symbol at the bottom, even the best countermeasure doesn't really do the job for you. You're coming back with a degradation in capability. Is this important? Is this going to lead to a bone fracture? We're not exactly sure. But the point I wanted to make, rather than throw in this little somewhat humorous interjection, was the fact that this is something that we deal with in the area of human research that sometimes our physical sciences and engineering colleagues don't appreciate. And that is the range, among other things, the range of human variability, not only across individuals, but over time, as we age. So the physicists tend to have this kind of viewpoint in trying to predict the behavior of blah, 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 whatever human system, just model it as some simple thing that they understand and add some secondary terms to account for, et cetera, et cetera, et cetera. How hard can it possibly be? After all, we're physicists. We have that this is the queen of the sciences, and all of your biomedical sciences are trivial in comparison. In so many words, that's sometimes the attitude that we sense. However, I have to say there are exceptions. Mary Gell-Mann, not an insignificant physicist, said, imagine how hard physics would be if electrons could think, meaning, of course, that when you start to deal with the human element, things become a little bit unpredictable, even if we understand the fundamental physical processes that might be going on in the body. Okay, so I've given you an example of some of the major things that could happen to people, that do happen when people go into space. So, two remarkable points. One remarkable point is, wow, almost everything is impacted. I would say every system, every body system is impacted some way. Some worse than others, some more alarming ways than others. But pick a system, and somehow that seems to be changed in space flight. The other remarkable thing is that even given all these changes, we send people up into space on a regular basis, and they do really well. They built a space station. They repaired the Hubble Space Telescope. They do incredible things up there under very demanding circumstances. So far, have we just been lucky? No, not really. I mean, the astronauts are very highly trained, and NASA and other space agencies put a huge amount of effort into ensuring the success of the mission. But they've also been relatively close to home, and they so far have largely met challenges for which they've been prepared. You could see that coming. It may not have been pleasant. There have been some exceptions, like the leaking spacesuit that started to get water in Luca Parmitano's helmet and almost drowned in space, because when you're in space, the water doesn't go to the bottom of the helmet. It has surface tension and tends to go all around your face, so you almost drown before he was able to get back into the space station. Okay, who would have expected that? But he did the job. He got back in before he died. So they're trained to some extent to deal with the unexpected, but NASA tries to limit the unexpected. Here is NASA's approach to doing this in the Human Research Program. This is the chart that basically ran my life when I worked for them for 3 years. This is something called the Integrated Path to Risk Reduction. This is NASA's way of, to some extent, addressing this. Addressing the fact that NASA is an engineering and operational organization to a great extent, but is trying to figure out how to deal with the variability and complexity of people and their medical concerns and issues. So, NASA has a very rigorous, often very contentious process. You can't argue about the process. It's a good way to do this in an engineering environment. So, the process by which they identify the main risks to human health and performance of long-duration spaceflight. And that's the list of about 15 or so. When I was there, the list was about 30. That doesn't mean they fixed the other 15. It just means they've reprioritized a lot of them and decided we either don't have the resources to deal with them, or maybe they're just not that important, or maybe both. So about 15 or 20 down the left-hand side, so you can see at the top space radiation exposure, space-induced cardiovascular disease. The third one, cognitive or behavioral conditions. Behavioral medicine, as NASA calls it, among other fields. That's the psychology. That's number 3 on their priority list. And you start sending people to Mars, 4 or 6 people in a small environment for a long period of time, far away from home, no way to turn around, and somebody might not come back because of a medical issue. Yeah, there's going to be some issues with maybe mood, depression, motivation, interpersonal relations. So NASA recognizes this. Astronauts, again, very special people, highly mission-oriented, highly driven, highly motivated, but still they're people. So you want to be able to address some of these issues before they impact their performance. Okay, the main point here is not the details of the, and by the way, it's a timeline, right? So it goes from the left outward, and I think they, look at that, they stopped even putting dates on. No, the dates are at the top, okay, yeah. So you have to squint to see them. But the idea is to get as much of this done within the lifetime of the International Space Station, which would be another, who knows, 8 years or so, maybe, if we're lucky, so that they can, NASA can say that they've mitigated these risks. They've taken the ones that are red, meaning relatively high likelihood, by high they mean more than 1% based on statistics that they can marshal, relatively high likelihood and bad consequence. Somebody's going to die from this or be permanently debilitated. Green is just the opposite, low probability and not so bad consequence. And yellow is in between. So the job of the Human Research Program is to take these red things, make them yellow, take the yellow ones, make them green, all within the lifetime of the International Space Station so that they can sign off and say, we're ready to go, we've mitigated the major problems. Now, anybody here who has done human research knows that this is not the way human research works. This is what we call a success-based strategy. If you wanted to be less charitable, we could say that this is something that's a useful fiction or maybe even completely unrealistic because things happen. There are things that are unexpected, like the SANS issue, the Space-Flight-Associated Neuroocular Syndrome. Now it's on here, but 15 years ago it wouldn't have made this list because we got the experience. So what's the next big thing that's going to happen when we start sending people into space for a year at a time, which NASA hopes to do more on a regular basis? So the other thing, though, about this is that it implies, within NASA, it more than implies, it instantiates, but for the rest of it, at least it implies that these are independent risks. So sometimes these are called swim lanes, horizontally moving across the page. You've heard other euphemisms, silos, stovepipes, and in fact, just like every other organization on Earth, NIH, even the Johns Hopkins School of Medicine, they generally, different groups study these different discipline areas. We're not yet completely in the area of multidisciplinary, cross-disciplinary research, which, as I made the point before, is what's going to be needed here, and I'll make that point again in a minute. So, in fact, in reality, these issues are studied, researched, and mitigated, mitigations designed for them by different groups within NASA, all within the Human Research Program, but otherwise largely different groups. But, as we all know, and as Ron White wasn't good enough to commit to publication 20 years ago, meeting the health-related challenges of human space exploration requires that one abandon the model of the human body that has muscles, bones, blah, 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 blah. Acting independently. Body parts will not travel on exploration missions. Instead, the individual space traveler's body must be viewed realistically with all parts connected and fully interacting. So here's just a trivial example. It's trivial to me because I use it over and over again. But CO2 level in the spacecraft, so far anyway, and certainly in ISS, is elevated. It's about 10 times what it is, hard to say now since I've been spewing this nonsense for close to an hour. So who knows what the CO2 level is in here. But typically, it's 10 times higher in the space station than it is on Earth. Why? Because it's expensive to scrub it down. It's expensive in terms of resources, consumable supplies, energy, and maintenance on the CO2 scrubbers. So they let it go up. But there are well-known consequences of elevated CO2 level. You can read about it in Scott Kelly's book. He talks about elevated CO2 and how he thought he could feel it exquisitely. and could definitely tell the difference when there were 6 of them grouped together in one place, like having a meal, and that the CO2 level in that compartment started to rise, or when there were 9 people on the space station, because 3 people went up before the other 3 came down, 9 people up there, an extra load, CO2 level goes up. So he said he could definitely sense that. So what are the consequences? Headaches, cognitive slowing, you just don't feel that great, don't work at your peak capacity. Vision changes, these are known from terrestrial studies for a long time. So that's the spacecraft atmosphere. So what are some of the ways that the body deals naturally with a elevated CO2 level? Well, at least 2. One of them, to buffer the acidity of the blood because of the elevated CO2, takes calcium from a calcium store. What's the calcium store? Bones. I believe I may have mentioned that they have a bone loss problem in space because of unloading, because of zero-G. So you have a synergistic interaction between 2 things, elevated CO2 and bones, which you would initially think should be different risks, but now they are related to each other. What's another way the body deals with elevated CO2? Elevated CO2 reduces the ability of the blood to carry oxygen. So what do? Well, you pump more blood to the brain to make sure the brain at least gets enough oxygen overall. Well, you already have a problem with fluid shifting toward the brain. Blood, cerebrospinal fluid, lymphatic fluid. So the last thing you want to do is pump more up there. And yet those are the ways the body naturally deals with this problem. So the natural compensatory mechanisms make things worse, potentially. So what is one of the ways that sometimes I title this talk, Human Health and Performance for Mars, the way NASA does it, the way NASA should do it. So this is the way NASA does it. Like I said, not necessarily a bad way to do it, but I think an incomplete way to do it because it neglects explicit recognition of the interactions, but also leads you to think that if you just mitigate the problems, then you are done because you've mitigated the problems that you don't know about. Well, what about the problems that you haven't identified? The problem that only happens when you're in space for 2 years and you're not going to see until you are on your way back from a Mars mission or already you're at Mars. How do you deal with that? Well, for that, you need to provide resilience for the crew to deal with the unexpected. Getting to that in a minute. But first, I need to show you the framework in which I think about this. So this is a way for me to set up something called the contributing factor map, which I fell in love with when I first saw it. It's not my work, it's the work of Jennifer Mindock. This was her doctoral thesis work about 10 years or so ago at the University of Colorado Boulder. She, until just recently, worked for NASA, so I met her in the human research program. And we still work together, or trying to work together on some projects. So this was her way of putting into an organized framework all of the factors, the contributing factors, the factors that contribute to the success or failure of a human spaceflight. And these are the general categories that I'm showing you here. So typically, physiological adaptations, psychological conditions, those would be the things that are in the domain of the human research program, the things that we normally, as biomedical researchers, would think about. Sometimes you don't even think about the psychological ones. I mean, you have to be tremendously open-minded as a medical researcher to be thinking about the close interaction of the psychological issues with the physiological issues, but of course they're there. And then there are other things, right? So go up to the top. Task planning and scheduling, training, shift scheduling, mission planning, you can read them. The way you design the mission, the way you design the spacecraft, the way the people in the spacecraft get along with each other and get along with mission control, get along with their peer groups, all of these things have a bearing on stress, among other things, which then has a bearing on psychological well-being, which then has a bearing on physiological and medical status. But also, there are feedback paths. Because if you have a physiological maladaptation that leads to an injury, that may impair your ability to, well, I don't know, maybe repair the CO2 scrubber, which then will put you in a vicious cycle to make that problem even worse, or repair the exercise machine on which they rely for a lot of things. So when you fill that in, it looks like this. So I will leave it as a homework assignment for you to look, read, and memorize this chart on your own. It's freely available online, or I can send you a copy if you like, or I'll send Mike a copy and you can distribute copies. Usually I carry paper copies with me, but I forgot them this time. But it was an eye-opener for me to see this because it brings with stark clarity the fact that all of these things, yes, all of these things are important. Some may be more important than others. But I also looked at it, and having a mathematical an engineering background, my background is biomedical and electrical engineering, these things are connected. Here it's a taxonomy, it's a categorization, it's a listing of all things, and they're put into categories, and there's some sense of how they might interact. But that should really be made explicit. That's what's missing. That's what I'm going to tell you about in the next few minutes. So I'm going to skip over this very interesting thing here, but I don't have time to get into that. Here's what I think should be done. Here's the how NASA should do it part of maintaining health and performance in space. So let's start with that contributing factor map. And I'm going to get back to that. This one. Okay. But what you don't see here explicitly is this stuff down here at the bottom, task performance outcomes, mission outcomes. They're kind of very broad categories down there. But like I said a number of times, you're sending people into space to do something, to explore a surface, to build something, to whatever it is. They have more or less well-defined tasks. Well, thanks to this report from Jack Stuster and his colleagues, now they have some very well-defined tasks. So Jack Stuster, this is, again, freely available, Human Research Program final report from a grant project or contract. Generalizable skills and knowledge for exploration missions. In other words, what are the things that crews are going to have to do when they get to Mars? That's what that title means. What kinds of things? Are they going to have to drag a 50-kilogram mass across the Martian surface? Are they going to have to lift such a mass over their heads to get into a spacecraft? Are they going to have to drag a wounded colleague in a spacesuit up a ladder to get into the spacecraft? Are they going to have to do what level of hand-eye interaction and fine manual motor control will they need to land the spacecraft? Or will it be completely automated? What are the backup processes that they're going to have to maintain? What level of vigilance? All of those kinds of things. Very voluminous report. And, it's the best estimate of the community at the time because he went out and asked a large number of subject matter experts and then categorized and prioritized the feedback. And so these are not a surprise, but these are some of the things that came up near the top of the list. It's a very long list, like I said. But this is an example. If you're, for example, science-related, this isn't broken down by specific tasks, but kind of categories. Science-related EVA, science-related extravehicular activity. Put your suit on, get outside the spacecraft, and pick up some interesting rocks on Mars. So that's a science-related EVA. That's a high priority. That's why you're doing piloting. Yeah, that could be pretty important too. Chances are the piloting operations, spacecraft operations will be highly automated under nominal conditions. But Mars descent and ascent, getting there, launching back, Mars orbit engine, parsed out by these specific mission phases. Interaction with the crew during Mars surface operations, which is what MSO is. So how is the crew out on the surface talking to the crew that has better situational awareness that's inside the spacecraft, the equivalent of air traffic control? Assess displayed information, EVA for maintenance on your way to Mars and on your way back, that's en route, performing medical diagnoses and performing robotic operations. That's just a small list, but those are the biggest priorities. They drop down in significance after that. Well, here's what really needs to be done. Take these major tasks, put them down here, most critical Mars tasks. So this is where I start modifying this. And then you can start making it a network and say, for piloting, what are the physiological things that are most important? So here you've got vestibular function, sensory motor function. Kind of makes sense. But you can do that for anyone. There's a certain amount of guesswork involved, but on the other hand, these are things that have been studied, kinds of things that have been studied in the lab, in kinesiology labs, and biomedical engineering labs, and a whole bunch of different types of labs for decades. So there's some good evidence by which we can populate this. And you can do it for the next level up on the physiological outcomes and map it to the same set of tasks. And then you've got a network. But you've also got the feedback loops that I was referring to earlier. So maintenance EVA, for example, feeds back here to the vehicle physical environment. If you're not physically capable of going out and carrying out a demanding spacewalk that might be required to fix something on the outside of the spacecraft that maintains the integrity of the inside of the spacecraft, well, that disability, it doesn't end here. It feeds back and it impacts that stuff at the bottom, at the top, which then has further downstream effects. So it is not a acyclic graph, as they say. It's not a one-directional graph. It's a cyclic graph. There are feedback paths. So what do you do with something like that? Well, here's what I think needs to be done, and what I'm doing, starting some initial mathematical work on. I think we need a network approach to being able to say, when is this network, the more complicated network, filling more lines, when is that network resilient and when is it fragile? When is that network going to collapse if we wipe out a couple of key nodes? And what does that versus what does that network need to look like so that we can wipe out a couple of key nodes, like take down the exercise machine, and still have it carry out the main critical tasks of the mission, which sometimes may include sacrificing a crew member, not deliberately, but not exerting a huge number of resources to maintain somebody's life at all costs. If you're worried about maintaining an astronaut's life at all costs, don't send that person to Mars. That's part of the trade-off that has to be made. So, okay, a network approach, the explicit recognition of the interconnectedness, making this contributing factor not into a network, that's generally lacking in biomedical research for reasons I discussed earlier, the lack of systematic multidisciplinary research on a large scale. Also needs to span domains. And by domains, I don't just mean physiological systems, I mean the engineering domain, the operations domain, the spacecraft domain, the physiology, the medical, the psychology. We need to capture the feedback loops, as I showed you. We can draw on, it's conjecture, really. This is an act of faith on my part. Can't do that. We can draw results from network theory and complexity theory to say something about that, because networks, once they reach a certain level of complexity, become complex networks, there are emergent properties that somehow spring into place magically, and the network is able to get the job done despite the fact that we might not know all of the details about every individual component of the network, which is going to be the case in human spaceflight, because there's no way, if we wait until we know everything there is to know about every one of those boxes, we'll never get to Mars. You have to go with incomplete information at some point and trust that if I design the network correctly, by designing the mission correctly, that this will still be resilient in the face of unknown, unexpected perturbations, even with imperfect knowledge. So, okay, in my last 30 seconds or so, I won't get into the math of this. It's too bad, it's really fascinating. But there is some work out there that shows that you can actually do this. You can actually make some meaningful conjectures, meaningful inferences about the resilience, the robustness, the strength of a network under perturbations based on the topology of the network, based on the interconnectivity, not so much the individual dynamics, but how things are interconnected. And the interconnections are things that can possibly be monitored. Let me give you one example. The connection between CO2 level and behavioral health. Maybe we build up a database that says that over time, during a Mars mission, gee, the computer correlates that when the CO2 level goes up, this person just gets annoying and cranky, this person gets tired, these two people start getting into a fight with each other. All right, we build that database up. We understand it. It's not pretty, but we understand it. Now, all of a sudden, the computer sees the CO2 level has gone sky high, and these two people are still acting like it, but these two people are getting along perfectly well. Is that a good thing or a bad thing? Well, it's different. It means the connection in the network has changed. Well, what do we do about that? Not completely sure, but we may have reduced the resilience of the network because there's a set of dynamics now going on that we don't understand, that we're not comfortable with. So, we have to do the appropriate math, I think, to be able to figure out how to monitor those things, how to monitor the topology, how to monitor the changes in topology, and just jump right down to the bottom here. Oh, I do have to make this point. Stress has essential element, right? I talked about stress before. Stress arising from the way you design the mission, from interpersonal relations, from all sorts of things. Stress is like essential elements or an underlying substrate in any network. And so here are the listing of some of the stressors: physiological changes, cognitive changes, isolation, confinement, immune system interfaces, automation, interpersonal relations. The fact that your body is changing in space, and maybe you're uncomfortable with that, you don't like that. But I'm saying, sorry to be overly cute, let's turn that frown upside down. So let's say that those same stressors might also provide some of the solutions to your problems. And for this, I'm calling on this idea of the extended mind, the book that I recommend. I recommend at least the first two chapters, which I've read so far, derived to some extent from an essay that you don't have to buy. It's really available online, called The Extended Mind, 1998, that our cognitive processes, who we are in a very real sense, comes from the fact that our mind, our mental processes are really embodied. So the way we move our bodies, the way that we interact with the environment, situated, well that's the environment part, but also distributed, the fact that how you interact with other people, that these, I mean it's facile to say, we all recognize this, but there's more and more research showing that this really changes, influences the way we think in very fundamental ways, which to me means those same things can provide some of the solutions, those very same things that the fact that you're in a strange environment. So that's the other side of situated, being environmentally situated cognition. The fact that you're having to get along with a small group of other people for a long period of time. But the flip side of it is that's a distributed intelligence. The fact that your body is changing and you're sensing that you might not like it, but that's an embodied, the other side of that is embodied cognition. Maybe you need to rely on what your body is telling you as early warning signals to maintain resilience of the mission. Okay, so this is what needs to be done on a Mars mission. Okay, figure out this long list. This goes way, this goes on forever practically. Figure out these key things that should be measured and monitored. Maybe they come from the contributing factor map. Figure out how to measure them. Okay. There's sensors for everything out there now, and if there's not now, there will be very dominant on talking. So sensor development is huge, and there will probably will be sensors for most of these key things. When you put them into some kind of magic algorithm that is built on the contributing factor map, turned into a network. That algorithm tracks the topology and just provides information to the crew, to the commander. And maybe it's very crude, broad brushstroke information. Like I said, the example I gave before, Commander, I don't get it, but I'm detecting a change in this pattern here. That pattern that you saw before, you might not have liked the pattern, but at least you understood the pattern. Now we're in a pattern that we don't understand. You might want to check this out. You might want to see what's going on. And maybe I can give you some suggestions. So, okay, that is where I will leave things. Thank you for your forbearance as I went over time and for your attention.